Hello, everyone, and welcome to this session of the 2019-2020 Learning Exchange Series. I'm your host, Lauren Cooper, and I lead the Forest Carbon and Climate Program at Michigan State University. We are very pleased to lead this year's Learning Exchange Series in partnership with the Forest Climate Working Group. If you are not familiar, the Forest Climate Working Group is a diverse group of forest interests with over 50 members, including landowners, industry actors, conservationists, academia, and those active with carbon markets. Okay, sorry about that. Working from home. The group has worked together for more than a decade to advocate for state and federal policies that work to ensure sustainable forest use and prevention of land use change. To get to today's speaker, I'd like to introduce Indroneil Ganguly, Associate Professor at the University of Washington School of Environmental and Forest Sciences, and Associate Director of the Center for International Trade in Forest Products. Today's session will focus on how temporal radiative forcing analysis has been used along with the functional half-life of different wood products to evaluate the impacts of wood products on global warming. From this speaker, we will learn about the important role that wood products play in enhancing the global sequestered carbon pool. And I should note that this is the first part of kind of a two-part webinar that the close of our series here, but this is wood utilization 1, and the next month we'll have wood utilization 2 that looks at the connection between harvested wood products and a landscape scale. Before we get started, we'd like to do a little bit of housekeeping details. A couple of points. If you are interested in automatically receiving registration details and information about upcoming webinars, please email forestc@msu.edu to join our mailing list. Attendees today are also qualified to receive 1 CFE credit from SAF. So if this is of interest to you, just to note that you'll receive this credit automatically if you've registered with the email address associated with your SAF account. But if you have any questions about this, please reach out to us at forestc@msu.edu. This session has also been approved to receive 1 CEU credit from ISA in either the Management, Certified Arborist, or Municipal Specialist category. So if you'd like to receive ISA credits, again, please reach out to us at forestc@msu.edu and we'll share the event code with you. As an FYI, this session is being recorded and will be posted to the web along with any supplemental materials such as the presentation slides. And this happens in the next week or so. If you've registered, you'll receive an email letting you know when this is available and where to find it. And just to note that all of our previous sessions are also on the web. So if you haven't had an opportunity to take a look, you're welcome to peruse and view any of our previous sessions. A quick note on Q&A. Our sessions are normally followed by a Q&A, and we normally reserve questions for the end. But today we will be taking a short break for any clarifying technical questions after the method section. So we encourage you to submit questions at any point. So any type of questions that pop up. We do suggest you use the chat interface. So there's a little drop down with a triangle next to it on your Zoom menu bar. And here, again, offer up questions at any point during the presentations. We will compile them and we will have a longer Q&A session at the end. But if there are any kind of technical or detailed questions that come up in the first half of the presentation, we will take the time for about 5 minutes to address maybe 2 to 3 questions before moving on. But again, if you have larger questions, feel free to submit them and we will just add them to the list at the end. If you are calling in on the phone to join the webinar today, but you do have access to email, you can also send questions directly to forestc@msu.edu and we'll add them to our list. And in case of any outstanding questions, which has been happening, we've been having some great conversations here. And so assuming that we'll have some outstanding questions, we work directly with the speaker to have these addressed. And so those will be posted as a PDF that can be shared, that will be with the presentation materials on our website when the presentation is posted. So we will get to your questions even if we run out of time. And so with all that background, Indroneil, will you please share your screen and begin today's presentation?
Yeah, sure. Thank you, Lauren, for that introduction. I think I'm sharing my screen now, and let's go to the beginning of the presentation. And I think you guys can see it. Lauren, a yes would be nice.
Yeah, looks great.
Okay, perfect. Thank you very much for that introduction. And as Lauren, I'm also working from home. I took over my daughter's bedroom because that's the most acoustically favorable for webinars. And at a high cost, though, I have to give her a whole paint set for renting it for an hour. So it's a high rental. Anyway, I'll talk about utilization, carbon storage at the building scale here. Primarily, what I'll talk about is more of the carbon benefits of wood products. And we do hear a lot about the forestry and how much the standing biomass in the woods or in the forest help with our climate change, but not so much about the wood products. And that's, I believe, is as important, or if not more important, of an issue to discuss in terms of forestry. So that's my topic of my discussion today. This is generally the flow of the webinar. I'm calling it recap of human-induced global warming. The reason I'm saying recap, I'm sure you know what anthropogenic global warming is. However, I want to put it in context with my presentation. I won't take a lot of time, I promise. I introduced a section, myths, misconceptions, or reality. It seems like I've been hearing for last few years, at least, everybody has a theory why wood is good or wood is bad, how to manage forests, and apparently nobody needs a degree in silviculture to tell you on how to manage forests. And just like all of my friends on Facebook, even they have flunked in their biology class, they know uh, how to mitigate the impacts of COVID-19. So, so anyway, I'll talk about, I'll raise some of those questions and discuss those. Some are reality, some are half truth, which are as good as false. Then I'll go over the global warming mitigating impacts of wood products, and I'll take a little pause after I introduce a few slides of this section for the questions. I'll let Lauren select those questions. I'll not invest more than 5 minutes in answering those questions. Primarily, if you have any burning questions that are stopping you from understanding what's going on, those kinds of questions would be answered during that 5-minute break. And then most of the questions I'll take towards the end. I do have some slides on Washington State's forest and the wood product industry and how we can use that model to Washington State. However, understanding that a lot of you are not from Washington State, even from the country maybe, I will just skip that section. However, I will make those slides available, but I will not go into detail and just not tell you guys how good we are here in Washington State. I would like to emphasize a little bit more on the next topic, is comparative building level life cycle assessment between wood-based building and non-wood-based traditional high-rise buildings. So I'll start with anthropogenic global warming, and I will divide into 3 parts. The first is the concept of greenhouse effect. We have been hearing it, and we kind of know it, but just to put it in context, because I will refer to the term radiative forcing, and I want you to know what I mean. So when the sun rays, the radiation from sun comes to the earth, it's a very high frequency, low wavelength radiation. It just penetrates through our atmosphere and hits the surface of the earth. Because of this lower wavelength, it does not heat up the atmosphere in the process of coming in. However, when it hits the earth's surface gets heated, and in turn, it radiates back the heat with a lot lower frequency and higher wavelength, which heats up the greenhouse gases like CO2, CH4 in the atmosphere. And that heat, then that particular CO2 molecule radiates that heat back and heats up the neighboring CO2 molecules. And this bouncing back and forth goes on, and it keeps our atmosphere warm. And that's a good effect, actually. If this were not happening, we'd have frozen to death, because at night it would be so cold that no human beings or uh, will be live. Anyway, so there's this is the greenhouse effect. This bouncing back and forth and the slow release of the heat is the greenhouse effect. Now let's talk about the anthropogenic emissions. So basically, whenever we're driving a car, fossil fuel based, or burning coal, or some kind of forms of fossil energy in our industrial processes, we are emitting CO2 and all other greenhouse gases back in the atmosphere, which increases the abundance of CO2 or greenhouse gases in our atmosphere. And what happens as a result of that, uh, the greenhouse effect becomes more acute. So in this particular, the last pane I'm showing, this slide shows what's a natural greenhouse gas effect. So uh, the sun rays hit the surface of the earth, and some of the radiation leaves, and it stays a little bit in our atmosphere, and in the process heats up our atmosphere. However, because we are contributing to additional radiative forcing, what's happening, a lot more CO2 is getting accumulated in the atmosphere, and our release of heat is much less. So that increases the global warming, or the greenhouse gas effect, and increases the temperature of the earth. So the solution is simple. We need to emit less, and we need to sequester some of those CO2 back in our vegetation, or develop a high tech device that sequesters all the greenhouse gas out of the atmosphere. Now, I'll talk about some myths and misconceptions and some reality, and how those perceptions kind of impact how we think about wood products, or non-wood products in that case. So the first one I keep hearing is the core definition of sustainable forestry is that we harvest today, we replant, we wait for 40 years, or any variation of that. It can be 20, it can be 80, and recoup some of the loss in the forest biomass over the years, when that carbon that we lose because of the harvest gets sequestered back in the forest biomass. I would say that this is a widely circulated misunderstanding myth. Um, if you see the way the the certification bodies think about sustainable forest management, and that's the same way I think we should think about sustainable management, is that we are harvesting less than what's growing in that particular landscape in any particular year. So it's not that we harvest today and wait for 40 years. We are harvesting less. If a piece of a landscape in any particular administrative unit, let's say a warehouse or own landscape, a forest, sequesters 10 units of biomass in a particular year, will harvest less than 10 units in that particular year and maintain the standing biomass in the forest. Now, that triggers an understanding, a shift in how we look at harvest cycles. This is an example of a GIS map of Grays Harbor County, which is one of the highly productive forestry counties in Washington state. And these are the green squares you see here are our forested plots. Now, this is a more simplified representation, and the color differences in these plots signify the amount of biomass or the maturity of the forest. For example, this is very dark, means um, it's an older forest or more mature forest, and may get harvested the next year or the year after. And the lighter ones are younger forest. And that's generally how the even age forest management happens in most of the plantation forest, especially in this county. Now, some of these plots, I highlighted 3, got harvested this particular year, let's say. However, so on an average in a 45-year cycle, there will be anywhere between 2 to 2.2 plots, 2 to 2.2% of the plots harvested every year. That means in this particular year, if you're harvesting 3 plots, we are not harvesting 97 other plots. So though the biomass in these particular plots we harvest going down to very close to zero, the biomass in the other plots, neighboring plots, are actually growing in that particular year. And that is what maintains our steady state land forest biomass. And going back, so generally in this region, again, this is a highly productive forest. We grow anywhere, we add anywhere between 12 to 14% of the standing biomass every year, and we harvest 9 to 11 percent of that. So we are leaving some additional biomass in the forest. So not only that the standing biomass doesn't go down, it actually increases a little bit, and I'll show you actual data on that in a little bit. So so that's how I would think about sustainable harvesting. The second myth or kind of perception I hear, and this goes both ways, is some people would say mature forests sequester a lot of carbon. Some people say younger forests sequester a lot of carbon. Uh, and it's so confusing for anybody. And I'm sure people who are architects, who are builders, they're all confused thinking, oh, should we leave the forest to grow longer, or we should harvest the younger forest? And the problem is of oversimplification. In the wood product industry, we do have this uh, problem of oversimplifying things just because things are very complicated. And sometimes oversimplifying creates more criticism and creates confusion. So the actual the best growing, the sweet spot is in the middle somewhere. It's not very young forest, not very old forest. In most of the cases, it's in the middle, 20 to 60 years, depending on the species, the soil type, the agroclimatic zone, and all those things. So that's where the sweet spot is 20 to 60 year age plantation. So here, let me introduce you with this two diagrams or plots I have in here. This one to the left, number A, is the carbon storage in a plantation forest, which the plantation is in 2020, what happens over the 120 years. And the B pane of this figure is the growth rate. So as you see, the growth rate starts increasing significantly as the plantation gets into that 20-year age cycle, and then it starts plateauing off at the 60-year age cycle, and then starts going down. So that's where the sweet spot is. And it's different for, again, regeneration forest or plantation forest. It grows a little bit faster, drops a little bit faster, but the other line is a little bit different. But so the real answer is neither one is true. You'll have to make sure that the forest goes into that maturity phase. Now, conveniently, both sides would argue about the accuracy of the models. They say, models are wrong. And to a large extent, I agree. Models are oftentimes very wrong, especially when you go to very old forests because of a very small data set available for those very old plantation forests. So let's see what the good thing about living in this time is we have been running some real world experiments in our forest in America for since over the last 30 years. And we can start seeing some of the results. So let's see what those results, real life experiment results shows. So here in this particular graph, I'll talk about this graph in detail, but let me talk about who are the bars represent. The corporate, those are the highly intensively managed forests who manage forests for production and sale, lumber production and sale, or any kind of wood production and sale. On the other spectrum, we have the USFS forests. which we do minimal harvest, and then the reserve forest, which there's absolutely no harvest in there. There's also another working form of working forest, which is also productive, is the DNR, the state-run forest, which are also managed for wood products, but they are less intensively managed, which means they let their forest grow a little bit longer, so a little bit longer rotation. And then the small private are in this particular category. Now, along the y-axis, we have metric tons of CO2 sequestered per acre per year. So how I'll read for the corporate, I will read that in any particular year, let's say in 2020, 1 acre of the forest land, and this is for Pacific Northwest, 1 acre of forest land in Pacific Northwest sequestered on an average 5 metric tons of CO2 equivalent per acre per year. Now, in that same forest type, we are harvesting a little bit less than 4 metric tons of CO2 per acre per year. So it's skimming from the top of what is growing in that particular year. And the yellow you see is the natural decay, mortality. There are other factors like fire and whatnot. Now, going back to my sustainable forestry, you see that in that particular year, it's growing, sequestering 5 metric tons of CO2 equivalent, but the loss that's getting out of the forest is a little bit less than 5 metric tons, even after factoring in death and decay. So if we are, this is getting emitted in the atmosphere, either dying or decaying or burning, and the rest goes in the wood products. Even if we burn, let's say, all of the wood products down, still it's not increasing the abundance of CO2 in the atmosphere in that particular year because we have sequestered more in that particular year. Now, going to the DNR forests, we see that it is also highly productive, but the productivity goes down a little bit because of the less intensity, and the harvest also goes down. The least productive is, of course, the reserve forests, which are not managed at all, which are primarily very mature old growth forests. And this is the only kind of forest that has a net negative here. It sequesters 2 units, but it emits more than 2 units in any particular year. Now, there's no harvest that happens there. Most of it's for insects, disease, mortality, fire, and all those things. However, they don't contribute to the wood products pool, and they have a lot more environmental benefit than carbon. So I'm not saying we should manage intensively USFS forest. I'm just showing a trend here that what happens to carbon. So going back to my myth, yeah, so older forest does not necessarily sequester more carbon. It is kind of the intensively managed forest, which kind of gets harvested in that sweet zone between 20 to 60 year zone. So now I'll just go to one last myth, and I won't spend a lot of time in it. And we talk about greenwashing of biogenic carbon. I don't know how many of you heard the term biogenic carbon. Biogenic carbon is any carbon that comes out from any organic or biological matter, like wood, green vegetables, animals, protein, animal proteins, and all those things all contribute to biogenic carbon. So how, and the greenwashing, the criticism is that fossil carbon is exactly same as biogenic carbon in terms of how it contributes to global warming. Then the whole carbon neutrality of biogenic carbon is just greenwashing, and we should stop doing that. Now, there are a lot of correct facts in that particular statement, but the conclusion is misleading and wrong. Here are what is right. Yes, chemically, fossil carbon and biogenic carbon are absolutely identical, and they contribute to equally or equivalently in terms of global warming in the atmosphere, everything else remaining constant. It is also true that not all biogenic carbon should be called carbon neutral. And I'll talk about some of the instances when. However, when carbon comes from sustainably harvested forest, then the CO2 can be considered biogenic carbon and can be considered carbon neutral. Look in this particular case, if you look at all ownerships, so what we are harvesting or what we are getting out of the forest is less than in that particular year what is getting sequestered. So we are not increasing the abundance of CO2 in the atmosphere by harvesting or by decay mortality if we are growing enough, if we are making sure we are growing enough. And that is carbon neutral in terms of global warming, because remember my first slide, the actual global warming is happening because we're increasing the abundance of CO2 in the atmosphere. Even if we burn all of it out, we are not increasing the abundance of CO2 in the atmosphere because we have sequestered more in that particular year. Uh, so yes, biogenic carbon from sustainably harvested forests can be considered carbon neutral. Moving on. So what's the difference between fossil carbon and biogenic carbon? So fossil carbon has no sequestration mechanism. Here all we are doing is extracting millions and years old fossil-based carbon from underneath the Earth's surface and emitting it back in the atmosphere. However, biogenic carbon can come from the decay, mortality, fire, or from wood products, biofuels or whatnot, and there's a good sequestration mechanism going on. And if this is balanced, then definitely this fossil carbon is definitely bad than biogenic carbon because it depends on the source. And as far as global warming potential is concerned, um, biogenic carbon, if that's coming from sustainably harvested forest, is carbon neutral. All right, so moving on to one of the papers I published where I look at these sinks or embodied carbons and benefits of wood products. Here's a link um, of the paper. I published it last year, and we do talk about wood products in there. Now, before we talk about this paper, I just want to give you a perspective of life cycle assessment, not making an assumption that all of you know about life cycle assessment. Um, Life cycle assessment is basically we're trying to assess environmental impacts associated with all stages or life cycle of the wood product or any product, commercial product, process, and service. And looking at the history, it started in 1960s. The primary focus was waste disposal, how best we can dispose. And then it went to energy and toxicity of chemicals used in manufacturing processes, and creating life cycle impacts and environmental impacts of single product or product groups. Now, all those, the bottom line of from 1960s till 1990s, all the applications were based on extracted material from nature, which is called cradle, and then and disposing after the functional life of the product, disposing everything that we extracted or produced back as waste, either as air pollution or soil pollution or water pollution, and we call it grave. So we are just measuring all the negatives. There's no sequestration aspect going on here. Now in 1990s, what happened? Greenhouse gas became an important factor. We started talking about it, and we started talking about renewability of carbon. And now there's a cradle, there's a grave, but then now we introduce this concept of rebirth. We are not only just extracting, we are also renewing that particular resource. How to factor that in to make it a fair comparison between all these negatives that we are trying to estimate in life cycle assessment. Now, the whole thing, we need to understand the positives, and we still haven't received a consensus on how to do this. And what my paper does is tries to evaluate or show a method on how to address that particular problem. Having said that, I will just quickly introduce my method. I will not introduce anything technical or too technical. If you want it to be technical, you can go back to my paper. that I cited there. So to be able to understand the environmental impact of wood products, it's important to know that the radiative forcing, just like a CO2 molecule or CH4 in the atmosphere contributes to global warming by capturing the heat or the radiative forcing capacity, when we are removing it from the atmosphere and putting it in a stored form in a wood product, we are doing exactly the opposite, a negative radiative forcing right there. So, so that's what we are trying to estimate in this particular model. So there's a sequestered carbon in products. Uh, and if there's more carbon sequestered, the better it is, because we are removing a lot of carbon from the atmosphere and sequestering in a wood product. Now, to be able to do that, we are also burning a lot of fossil fuel, fossil emissions. We are harvesting, we are transporting it all over, we are using glues and whatnot, and we are adding all the negative, and that's why it's red. So there's the positive, more carbon, positive, and a lot of fossil emissions, negative. And the third aspect is how long we are keeping that sequestered carbon sequestered within the wood products. Is it 30 years, 10 years, or 100 years? If it's sequestered for 100 years, it's much better if you sequestered for 10 years. So there are two positives in here, which is amount of carbon and the longevity of the product, and the negative being the emissions that we are producing to be able to attain that positive. So what's the net benefit? So I will pause there uh, for a brief moment, and I'll see if there are any questions that I need to answer before moving on. Lauren?
Yeah, thanks, Indro. So we are getting some questions here. I think that one of the points from some folks in the audience is to clarify the difference between sequestration and storage, and how does the graphic that you showed with the FIA data and the different land use types, how does that, just to clarify, what aspect is that demonstrating?
That's a very good question. Let me address that going back to that particular slide. So here, this is annual sequestration. So sequestration is what the act of the woody biomass or the forest sequestering the carbon from the atmosphere, and the storage is what stays in the forest. So this particular graph only shows annual sequestration. It does not show what's already in the forest. And I'll talk about that, the storage, in a little bit later on. But this definitely talks about the annual sequestration and the annual removal of decay and mortality.
Okay, that's great. I appreciate that, because there are a few other comments which maybe to just plant this idea to touch on later on when you talk about pools. There were some questions about not including pools of carbon in that graphic, like soil and dead wood pools. So maybe if just to put that out there, if that's a point that you can clarify later on, how do you think about those other pools of carbon when you're thinking at a forest scale? Another detailed question was a clarifying of your use of the word cut, and just checking if you mean, clarifying if you're using the term cut as a harvest, or if you're distinguishing cut from a harvest in some way.
Okay, so let me answer the first one, which is different pools of carbon. One of the graphs I showed earlier, I did not mention all the lines here. It does talk about some of the other pools, which are soil carbon and deadwood in the forest. However, the recent FIA data where I got this graph from, they do have a really good data on soil carbon. So just stating from that particular study shows that soil carbon, independent of the forest type, has shown to be same between forest types. This different forest type soil carbon has stayed same. And in the previous graph, you can see some of the soil carbon or root carbon sequestration there too, and also litter and dead wood on the forest. There's a lot of data out there. If there's interest, I can share that FIA paper with you to dig into all those individual details. And sorry, Lauren, can you remind me of the second question that you had?
Sorry, yeah, it was a more of a clarification on your use of the term cut, and if you
Right.
mean something distinguished from harvest.
No, cut in this case is harvest. It can be harvest, it can be pre-commercial thinning, it can be um, fire hazard reduction thinning. It's all kinds of cut. It's harvest plus all kind of fire reduction thinning and hazard thinning. All those are included in cut. Um, Hopefully that answers your question.
Yeah, I think that was clear. Thank you, Indro.
All right. So if there are no more, Lauren, I can move on.
I think that, yeah, why don't you move on for now, and I'm going to circle back around on some of these outstanding questions at the end.
Perfect. Thank you. So now this is a single cycle. What happens in a plantation forest? And again, this was modeled based on Grays Harbor County, which is again a highly productive forest land, that county, and primarily Douglas fir. So this model is for Douglas fir in Site Class Index 1 in Grays Harbor County in Western Washington. So the left-hand side of the graph shows standing biomass in the forest over a 45-year period. You can see that the first 15, 20 years, the carbon storage in the forest is very low. So, and this shows the carbon getting stored every year and accumulated carbon. That rate of sequestration increases significantly at the 20th year and goes like at a steep rate till they're harvested at the 45th year. Now, can this be increased, the rotation, all those things are different questions I'm not addressing particularly. I'm just saying what's happening in this particular scenario. And 45 years harvest cycle is kind of common in this region. So I took that harvest cycle. Now, after the harvest, what happens? A lot of the wood gets wasted in different ways. The 4-inch tops, the barks, um, the branches, all gets left behind either in the forest to decay, or they're piled and burned on the forest floor. And then of the logs that end up in the sawmills or in pulp mills uh, or plywood manufacturing facilities, a lot of that also gets disposed of by burning as hawk fuel and energy, and that takes off more than 50% of the above ground biomass. The rest, however, gets converted in some kinds of products. So yes, it's true that we do, as soon as we harvest, we do lose a lot of the biomass in the forest in the process of converting some biomass into wood products. And if you look at the yellow on the right side, that's lumber. And if you see that it stretches on long, that based on the half-life analysis undertaken by US Forest Service, which says that the half-life of lumber, softwood lumber produced from Pacific Northwest is generally 38 to 40 years. So which means half of all the lumber produced is still in circulation after the 40-year mark, and then some lumber stays in use for a long time. Some gets wasted or ends up getting in the landfill. Uh, and and the height of the yellow at the starting is the fraction of all the wood products that goes into the lumbering facility, and that's based on Washington State's mix or Douglas fir mix from that particular area. So looking at, so this is a positive. This is a sequestered carbon that was sequestered from the atmosphere in the standing forest. And this is the carbon that stays sequestered in form of some kind of wood products. Now, bringing the negative, which is down here in the negative axis, is the amount of fossil fuel or global or greenhouse gases we emit um, to be able to convert that wood into a wood product. So if you see, and the color shades correspond to the product under consideration. If you see, this is the yellow is the product side or the beneficial side for lumber here, and then the thin slice of yellow and here is the emission, the fossil fuel emission or greenhouse gas emission that happens to produce lumber, and that includes the harvest, the transportation and everything in there, all the fossil fuel burns that happens. So you see that that is very skinny line, which is really good. So we are producing a lot of lumber with a very little amount of fossil emissions. However, paper here, you see, it's only a small portion slice of the overall product mix, but in terms of emission mix, it's significant. In case of other miscellaneous product like OSB, plywood, it's kind of, it has a long life, but also it does emit a lot of fossil fuel, especially coming from resin, and all the high processing goes on. So in a 100-year life cycle assessment, you have seen most of the life cycle assessment is global warming potential, 100 years global warming potential. What it does, it takes a slice of all the emission that happens and how they stay in the atmosphere and produce radiative forcing over time for 100 years. So that's the negative side. And remember when I told you the definition in history, that's all they were focused on the negative side of uh, this particular graph, how much we are emitting and contributing to global warming. On the positive side, we have the good. And in my model, I'm trying to show how the good can be factored along with the bad to see the net impact of wood products. So here you see that all of the wood products, the blue lines here are without considering the emission for lumber here, and the purple line is after considering the emission. And you see there's a little bit a drop in the net impact, but the net impact is still beneficial for the environment. That means we are mitigating global warming by this amount. All the products are net beneficial based on my analysis, except paper. Paper is not net beneficial because it has a shorter lifespan and it has a higher level of emission. However, in the net, our forests are net beneficial, and paper can be kind of linked to lumber and everything, because if you don't have paper, we don't have lumber. It's part of a system. In the net, we're a net beneficial. I did that particular analysis for Washington State, but I will skip that particular analysis. I'll make that available for you to go over, and it's in the paper, but I'll not go into detail. What I'll here mention is how we factor in multiple cycles. So this is multiple cycles. This is harvest happening in 45th year, and then apparently we go from a net positive to a net negative uh, after factoring in all the emission that happens in the wood processing industry. By 9th year here, we go back in the net positive after harvest, and then this thing goes on and on for years. However, that's a plot level understanding. Remember, coming back to the landscape level understanding, which I introduced initially, at the landscape level, it never goes back to negative because all other forest is positive. Some forests can have as high as 162,000 kilograms of CO2 per acre per year, but the average comes out to be around 50,000 kilograms of CO2 per acre per year for this particular type of forest land with Douglas fir plantation. However, when we factor in the wood products in the mix, we actually never have this negative. We stay in the positive even during the worst time, and the overall net benefit, overall impact of per acreage increases from 50,000 to 106,000. So what we can conclude is, number one, plot level understanding is only a partial understanding. We should think about the landscape level, because that's how the certification bodies think about it. And um, the wood products can contribute to even more. It actually, the beneficial impact doubles if you factor wood products in, as compared to just if you consider the standing biomass in the forest. So it's as important, if not more important. So this is the Washington State's scenario. I'll skip. I want to finish it in next 5 minutes to have at least 10 minutes left for some questions. This is important because in Washington State, there was a bill passed last month, a bipartisan bill, where they used my paper to justify why wood products do contribute to reducing the global warming in the state, or reducing GHG emissions in the state, and consider the beneficial contribution. However, I will skip that and move on to the building level analysis, which you guys may find more interesting. However, it's available to you. So again, the comparative building level analysis, we did a CLT versus traditional building, 8-storied. We published this paper in Journal of Building Engineering, and I provided you the link if you are interested. In this, what we did, we found a recently constructed building in Seattle using traditional means. We took the functional aspects of that building, and we worked with architects, that particular architect who built that building, and the builder, and also an architect at University of Washington, Kate Simonen, who created a model of a CLT hybrid building, or a few CLT hybrid buildings, and comparing the traditional building and the CLT hybrid building and the carbon storage and all those aspects. So here I'll be we in this paper we published, we created a lot of building configuration, but we found 3 to be the most useful. The first one, number one here, is the reinforced concrete building, or traditional building. The second one over here is a CLT hybrid building with fireproofing. Fireproofing is when we use a gypsum fireproofing to mitigate fire risk. The third option we model is called a charring design. Now, charring design is a very interesting design. It's used for a long time. People have been using it. What we do, we put sacrificial layers of wood outside the CLT panels, let's say, our glue lamp beams. And we are overbuilding with wood. What happens if the structural design requires a 3-ply, would put 5-ply, because in case of fire, the outer plies will burn and charred wood is a natural insulator, stops fire from going in. And they have been doing this in glue lamp beams for ages. We can do that. So basically, we are overbuilding with CLT in this third option, charring design. So if you see in the reinforced concrete building or the traditional building, we are using a lot more concrete and steel rebar, comparing these, than in CLT building. We are using CLT and glue lamp to offset some of the steel and concrete that we are not using. And in this particular, we are using gypsum board for fireproofing, whereas in this, we're using a lot more CLT for fireproofing. So the third design uses a lot more wood. Let's quickly look at what happens with the life cycle assessment. We are net beneficial in almost all the criterias here, and this is almost a flush within a 5% error rate. Here we see that we have a significant reduction in global warming potential, which is 26.5%. And this is only the embodied carbon, how much less fossil carbon we are emitting, or how much less greenhouse gases we are adding to the atmosphere. However, when we look at all the wood that is sequestered, we are sequestering a lot more in the charring design than in the non-charring design. And then applying my model, what we see here, that actually the benefit, when you consider both the sequestered benefit of wood and the reduced embodied carbon, it can go down up to 72%, 50 to 72%. And some of the more recent analysis we have done, we are working with Susan Jones on a new set of 8, 12, and 18-story building. And we are seeing that reduction is even higher as we are learning more better on how to build with wood. So in summary, the wood products emit less greenhouse gases, and the sequestration benefit, uh, especially at the building scale, because the wood stays sequestered for really long. In this case, 80-year scenario, we get a lot more benefit just by considering how long the wood is getting sequestered and mitigation impact. That's all I have. I need to give a shout out for my co-authors, Edie, Francesca, Cindy, who helped me with this paper. I should also say Kate Simonon also helped me with the architectural model at UW Department of Architecture. With that, I'm a little bit over time, but I think we have some time for questions. Thank you.
Thank you very much, Indro. We do have a number of questions here. So I'm still figuring out the best order for these, but I think maybe one we could start with some clarifying questions. If you wanted to go back to the single cycle factors considered graphic that you have, we have a couple of questions about this graphic. One was looking at this graphic here, what would the post-harvesting, actually might not be this one, but the post-harvesting graph look like of if some of the residues went to biomass energy? Is that incorporated here?
That's an excellent question. So what you're referring to in general, I would say that's a substitution effect. So a substitution effect is what we did not, so there are two kinds of, are there few kinds of life cycle assessment. This is called an attributional life cycle assessment, just estimating what's happening. Now, I have other papers on biofuels where we see that if we are converting that residue into biomass and into biofuels, and what that will do is offset the use or reduce the use of fossil-based fuels. And what is the net benefit? Because we do burn fossil fuels and to create biofuels, but we are reducing the use of fossil fuels at the end. However, that substitution effect is not included in here. And if we include the substitution effect, like the ones we included in the CLT building, the impact, the beneficial impact, what we see here for Washington State in general and wood products industry in general, will go up significantly. But that's not included in this particular graphic.
Great, thank you. Another question about this graphic is why, just for the data analysis, why does it extend out past, so far out the 200 and almost 300 years? Could you just explain the constraints there on that?
Yeah, we can stretch it out as far as you want because it's a half-life model, and then CO2. Some of the technical note on CO2 is that CO2, what we emit today, would be still 50% of that will still be in the atmosphere of 100 years from now, unless there's a sequestration mechanism. So, and the wood products or forests do provide that sequestration mechanism. However, though we can model it in a stretched out way, what the life cycle assessment based on the UNIPCC does is cuts out only the 100-year portion and integrates the negative impact for only 100 years, and that is the 100-year potential. So we can stretch it out for modeling purposes and cut it out as is necessary based on the standards we are using. In this case, we are using the IPCC 100-year standard.
Great, thank you. And we are getting a couple of questions still about soil carbon and dead wood and litter storage. And so I guess I'm wondering if you can clarify how those forest impacts or those forest pools are included in an LCA analysis like this.
So one of the things about soil carbon is one of the trickiest topics, because first of all, let me say this: independent. There's a lot of soil scientists at UW, and different universities who have been studying soil carbon as a result of different types of forest management, harvest, not harvest, compact, burning, broadcast burning, slash burning, and so on and so forth. What we have seen that over time, the soil carbon stays constant, and that's a huge mystery. We don't know in forests, different kinds of forests. And the FIA study that I referred to also showed, and unfortunately I don't have that graph handy right now. Maybe I can, but we don't have time. No, I'll skip that. But it stays constant over time. What we don't know is deep soil carbon. All these roots, when they decay, are they going into deep soil? And there's a lot less data on deep soil. So what we can say that the topsoil does fluctuate a little bit, but in the long run, independent of the harvest practice, if we are still talking about forests being forests, independent of the forest types and harvest practice, the soil carbon kind of stays constant and does not change. And that's why we can safely not include soil carbon, but there's a lot of entropy. We don't know what happens in deep soil, and that's a big unknown.
Thanks for that. And another kind of related question here is looking at that net, which is now in the bottom corner of the current slide, where you highlight some of the contributions or the emissions that are occurring. But this question is about, isn't some decay and natural breakdown necessary or good for forest health? And how would you think about that balance of having, you know, some material that provides various ecological benefits but is contributing to slowly decomposing? How do you address that in your work?
Yeah, that's a good question. That gets addressed more when we talk about the slash fill and how we what we do with post-harvest residue. And in the Nara Biofuels project that I worked on, we did a lot of work. There's some amount of litter that we need to leave on the forest floor to maintain that organic process that goes on, natural process. However, the burning, the broadcast burning does take care of some of those. If there's too much litter, then new seedlings cannot grow, and so some natural fires are good. Taking away some residues and burning them is good. Otherwise, they add to the potential of wildfires. However, we should not take a lot of forest residue out of the forest floor, and that limit is 15% for Pacific Northwest. It may be a little bit higher for some drier climates, but generally we never take more than 50 or leave a lot of the residue, let's say, on the forest floor for that system to go on. But that is not relevant for this particular study, because if you see the black over here, that's the residues that are on forest floor and decaying, and we did model that, and that is important and for the forest regeneration.
Thank you very much. We are getting pretty close to the hour here, so I'm going to ask kind of a larger question. Well, there's a specific component and then maybe a bigger picture kind of closing aspect. This question is about just first of all, how applicable do you think that some of these estimates are for individual products? For how applicable do you think that the study is in terms of thinking in other regions of the United States or other states, for example? And then generally, where do you see this research going and the needs going forward for both the Pacific Northwest and in other parts of the country?
I think that's an excellent question. Based on the national data I've seen, I'm not an expert in other regions, so I'll be careful how we talk about it. But generally in the US, we have seen our forest standing biomass is going up in the working forest, which is a sign that we are sustainably harvesting our forest. However, I am very careful whenever I talk about the carbon neutrality and sustainable harvesting. It's important to create the demarcation. Number one. Second, I think we need to think about forest as wood products as a system, just like we have here, that in this particular graph, you can see that lumber is actually what is helping in the good environmental profile of the forest. And that's because we are producing lumber at a lower impact, and we are keeping it sequestered for a long time. And hopefully with CLT, we extend this half-life of lumber, and then the beneficial impact of wood products industry goes even higher. However, I would warn against thinking that, oh, paper is bad, because there is an article I saw that paper is important for lumber, and lumber is important for paper, and all the bath tissue that we are running out of in COVID-19. So it's part of a system. We need that for economic bottom line, and take that cost, environmental cost, as part of the system.
Thanks so much, Indro. This has been a really fascinating presentation. It's certainly very timely. There's a lot of exciting work happening in this space and a lot of questions about carbon. So really appreciate the time that you spent with us today and sharing your research and answering questions. We do have some outstanding questions here, so we will be organizing these kind of thematically and following up with Indroneil. And we will post a PDF with some written responses. So thanks in advance, Indro, for taking the additional time to answer some of those more or additional questions as well. But thanks to everyone who joined today. We really appreciate the time. Great questions coming in. Really exciting topic area. Just a quick note before we all head out that we do have one more session coming up with Mark Wishney on June 3rd, looking at wood utilization again at this higher scale, so looking at land use and even a global outlook on what increased deployment of mass timber could mean to carbon across the landscape. And so with that, we will be in touch when the recordings are available. And thank you again to our speaker, and thanks everyone for your time. Have a great rest of your day, and we'll see you in about a month. Thanks again, Indro.
Thank you.